Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today we're going to take a look at how to graph sine and cosine functions. This section is like our traditional transformation section, where we talk about the parent functions of the graph and how to transform them. So it would make sense for us to first start talking about the parent functions of sine and cosine graphs. So over here, I've got this graph here. You'll see in a second why I made it so long instead of tall, but this is what we're going to graph, y equals the sine of x. So where do we begin? Well, first things first, we need to figure out what markings should go on this graph. Obviously, we're going to start at 0, 0, but should we count it by 1s, 2s, 3s? We'll get to that in just a second. For now, let's figure out what the value of x is, what sine is, when x is 0. So if I wanted to find y equals the sine of 0, for instance, this at first seems like a bit of a problem. I mean, how do we find the sine of a number like 0? Well, we have to remember a little trick we found when we were dealing with our unit circles. The rule that'll help us here, I'll put it in this top corner, is as follows. The sine of any angle, theta, equals y over r. That's what we talked about last time. It's like opposite over hypotenuse, but not quite. When we're dealing with a unit circle, what was our r value? Well, when we were dealing with a unit circle, that was just y over 1, meaning the sine of any angle is equal to just the y value of its point on a unit circle. So we can actually use our unit circle to find the sine of 0. If we look on our unit circle, we can look at 0 radians, and we see the point 1, 0. Since sine equals y, the sine of 0 is 0, the y value at that point. So we've got our first point, right here at 0. Now, I could plug in a bunch of other radian values for x. I could find what sine of pi over 6 is, that's 1/2, or pi over 4, that's root 2 over 2, or pi over 3, but that's root 3 over 2. I kind of want one that's a little bit nicer, not a fraction, just a whole number. The next whole number measurement we get is at pi over 2 radians, and the y value of that point is just 1. So, the sine of 0 was 0. The sine of pi over 2 is 1. I'm going to choose to make that my next measurement. So at pi over 2, we go all the way up to 1. I'll call this marking on our graph 1. So as we look at this, we might think, oh, this is going to be a straight line going up. It starts at 0, and then it goes to 1. So maybe it'll go to 2 next. Let's see. The next whole number measurement for a y value here is at pi radians, -1, 0. So the sine of pi is 0. Oh, okay, so it didn't go up again, it sort of went back down to 0. Maybe this is a parabola then. Well, let's keep it going. The next whole number we get is at 3 pi over 2 radians. The y value there is -1. So far, so good. We just have to put in a -1 here. We'll plot our point right there. So maybe we're right. Maybe this is a parabola. It sort of looks parabolic. But the next whole number after 3 pi over 2 repeats. It goes back up to 2 pi radians, which is the same as 0 radians, which we said was 0. Okay, so definitely not a parabola. In fact, this graph sort of goes like this. Sort of curves up to a point, goes down through here, down to this point, and then sort of continues back up. This is a really funky looking shape. It goes up and then down, and then it starts to go back up again. This shape alone doesn't really give us too much information. So I want to see if I can actually expand our graph in this direction or in this direction. Let's start by actually going backwards. So if I wanted to go backwards from 0, I could count to negative pi over 2, then negative pi, then negative 3 pi over 2, then negative 2 pi. So what I'm really doing is I'm working my way backwards, because remember, negative angles are the same as their normal angles, just in the clockwise direction. So to go from 0, right up here, to negative pi over 2, I just have to go a quarter turn away. That's the same as 3 pi over 2. That was negative 1. So we know that negative pi over 2, it's at negative 1. If I keep going clockwise, we notice that our next point is at pi radians. That's at 0. So we hit our x-axis. Then we go up. It's at 1 again, so we go up to the very top. And we start to see a bit of a pattern form. This curve is going to go up to a point, then down to a low point, then back up again to a point. Hey, wait a second. The left side of this graph looks exactly the same as the right side. It's like it repeated. So what if I went even further on this graph? What if I kept counting up by pi over 2's? We got pi over 2. Pi is the same as 2 pi over 2. 3 pi over 2. 4 pi over 2 is the same as 2 pi. What if we counted to 5 pi over 2? 6 pi over 2 is just, if we did that and reduced it, it'd be 3 pi. 7 pi over 2. 8 pi over 2 is the same as 4 pi. Well, guess what? It's going to repeat yet again. We're going to have a high point, a middle point, a low point, a middle point. It's going to go and repeat. Up, middle, down, middle. So what's going on here? The graph of sine will repeat over and over and over again. Kind of interesting, right? Let's investigate some of the features of this graph before we go on. The domain of this graph is pretty clear to see from its depiction. Our domain is all real numbers since it's never going to stop. It's going to continue going in this pattern to the right, and it's going to continue going in this pattern to the left as well. But the range is interesting. We're almost ping-ponging in between, the top being 1, the bottom being negative 1. 1, negative 1, 1, negative 1. And we never go past that. So our range is everything in between 1 and negative 1. It's negative 1 is less than or equal to y, which is less than or equal to 1. The next thing that I want to take a look at is something we haven't actually seen before. So remember how we said the maximum values were at like pi over 2 comma 1, or 5 pi over 2 comma 1, or even at negative 3 pi over 2 comma 1. Our maximums are all at 1. Our minimums are down here at the bottom at negative pi over 2, negative 1, or 3 pi over 2, negative 1, or even all the way over here at 7 pi over 2, negative 1. Our graph just keeps on flipping back and forth between top at 1 and the bottom at negative 1. So, when we take a look at this, each of these peaks, each of these mountains that we've made, gets 1 away from the x-axis. This is a width of 1. So is the bottom portion. It's also a width of 1. What's the deal? Well, we have a name for this. These sort of humps, or at least the height of them, is called the amplitude. The amplitude of a graph is going to be the distance from the middle of it to the maximum or the minimum. This would be our amplitude of 1. Very nice. So from here, we have a lot of features of this graph. Something else that deserves to be mentioned is the fact this graph repeats over and over and over again. It goes up and then down and back to middle, up, down, back to middle, up, down, and back to middle. Anything that repeats like this, in nature we call a cycle, like the water cycle or the lunar cycle or anything. Anything that repeats is called a cycle, and the length of a cycle has a very special name. It's called a period. You might have heard like a periodic table. So when we say a period of a graph, we're talking about the portion that repeats, and we can copy and paste to the left and right, and the graph will look the exact same. So you see how here we go up, then down, and back to middle? We go up, then down, and back to middle in the red as well, and in the purple. That is one cycle, which we call the period. The length of the period is how far it takes before we have to repeat. And to go from 0 to 2 pi, we would say our period is 2 pi. The period here is 2 pi. Now, what's most interesting about this period is it takes exactly one period to go from a maximum to another maximum, or a minimum to another minimum. To go from negative 3 pi over 2 to 1 pi over 2, we're moving 4 pi over 2 up. Negative 3 plus 4 is 1. Well, 4 pi over 2 is just 2 pi. So actually, between maximums, we go exactly one period away. Same with minimums. The minimums are also one period away. But what about the x-intercepts? Well, we can see here that in each period, we get 2 more x-intercepts. What that means is that every half period, our x-intercepts will repeat. So our x-intercepts are going to repeat every half a period. It starts when x equals 0, but we also get one at pi over 2, and since we have one at negative pi over 2, I'll say plus or minus pi over 2. We have one at 2 pi, so that's another pi over 2, plus or minus 2 pi, plus or minus, I'm sorry, I just completely said misinformation. We don't have one at pi over 2, we have one at pi. I totally miscounted that. One at 0, one at pi, one at 2 pi, one at 3 pi, one at 4 pi. We're basically just counting up by pi to get to the next x-intercept. So this is the sine graph and all of its features. Let's see if we can apply the same logic to the cosine graph. So here's what I'd like you to do. I'd like you to pause the video here and try to see if you can use your unit circle to find the cosine of all of those same values. Again, we're still going to be using 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. As you go through and do so, here is a hint. Remember that according to our rules that we learned last class, the cosine of any angle theta is equal to x over r, and if our radius is just 1, like we're using our unit circle, that means the cosine of theta is just the x value of the point on the unit circle. So look at your unit circle, look at the x values of all of those points, and see if you can use them to graph cosine. Pause the video and try it out. So how'd you do? With this, we can actually start graphing our points. So let's start off by finding the cosine at 0. If we wanted to find the cosine at 0, according to our unit circle, the x value at 0 radians is 1. So actually, this graph is going to start up here at 1. I'll even mark that off on the graph so we know what we're talking about. Which means you might be able to predict the lowest we'll ever go is probably negative 1. But as we continued, we should have seen that the cosine of pi over 2 was 0, so it went down to 0. The cosine of pi was negative 1, so we went all the way down to negative 1 as predicted. The cosine of 3 pi over 2 was 0 again, and the cosine of 2 pi, well, that's the same as the cosine of 0, that's back up to 1. So what's going on here? Well, we've got this graph segment that seems to go down and then back up again, but we know that this should repeat if we went to the negative values. So not only is it going to be like this with these values, but it's also going to work with the negative values, like negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. So it's also going to go back down to 0, back down to negative 1, back up to 0, back up to 1, in this direction. It's going to look like this. And of course we know it'll probably go down again. And in this direction, it's going to keep going like this. It's going to go back down again. So what's going on here? It looks very similar to the sine. In fact, if we wanted to find the domain of this graph, we would also see that it goes on forever. So it's all real numbers. If we wanted to find the range of this graph, it again seems to only go to 1 and negative 1. So negative 1 is less than or equal to y, which is less than or equal to 1. If we wanted to find the amplitude, that's also the exact same. I think we're starting to see a pattern here, because the highest it ever goes is 1 up from our x-axis, or from our middle. The period, it repeats every 2 pi again. 2 pi. The only thing that's different here are that our x-intercepts are moved around. Like, our first x-intercept isn't at 0 like sine was. I'll even put it up so we can compare. The first x-intercept is at 0, but this first x-intercept is at pi over 2. So we'll put down x equals plus or minus pi over 2. The next one's at 3 pi over 2. So we can keep on adding another 2 pi over 2 to find the next intercept. According to this, there'll be another one at 5 pi over 2, which looks like it'll make sense, and 7 pi over 2, and so on and so forth. The graphs of sine and cosine, then, are the same graph, just shifted over. Like, if I put these on top of each other, we see that they look like they're the same shape. If I just shift it over a little bit, not only are they the same shape, they're the same shape and starting at the same point. What this means is, if you want to go from a graph of sine back to a graph of cosine, you just need to move your sine to the left, pi over 2. So that's something that's really important here. As we go back to the notes, we see that for sine and cosine, everything is the exact same. It's just that the x-intercepts will appear at different places. So let's flip the page and see what we can do with these. As always, as with any type of unit we've been doing, we can also do transformations. Vertical stretches, vertical shrinks, horizontal stretches, horizontal shrinks. If I multiplied my entire equation by some number a, what would that be? Well, since we're multiplying the entire thing by a, it's vertical. But there are two types of vertical. There's stretches and there are shrinks. Oops, didn't mean to pluralize it. we learned that when a is bigger than 1, it's a vertical stretch. When a is less than 1, it's a vertical shrink. If I multiply just x by some number, that would be horizontal change. And we remembered that for horizontal, it's flipped. The stretch is when it's going to be between 0 and 1, and the shrink is going to be when it's bigger than 1. Let's think about how this might change our graphs. So let's look at our sine graph, and let's imagine that I pulled on these 2 points and I stretched it out vertically to be twice as tall. What would change? Well, if it was twice as tall, meaning it would have a point up here at like maybe 2 and down here at like -2, it wouldn't change the period. The graph would still go up, then down, then repeat after 2 pi, but it would change the amplitude. Our peaks are no longer 1 away from the middle, they'd be 2 away from the middle. So we say that the amplitude of a graph is just its a value. The a value in front of your sine or cosine graph is your amplitude. If it was 3, that means we stretched out to be 3 times taller, so your amplitude is 3. If it's 1/4, that means we made it a quarter of the height, your amplitude is 1/4. What if instead of stretching this out vertically, I stretched it apart horizontally like an accordion? I made it so it's wider. So here's the original, and then I stretched it so it widens out. Well, if we stretched out to be wider, our period would also stretch out. Instead of going from 0 to 2 pi, if I stretched this out to be twice the length, it would really go up, down, and repeat after 4 pi. So horizontally stretching and shrinking affects the period. The formal way we write it is the period of our graph is 2 pi divided by whatever our b value is, or at least the absolute value of b. Remember, if it's negative, that just means the type of reflection. So we need a new way of approaching this graph because we might get some weird values that don't fit on our unit circle. The good news is, with transformations, we've always done it based on the parent function. So if we have a parent function of cosine, we know that we're going to have a point at the maximum here at 0, then it reaches the middle, then down, then the middle, then up again. If our parent function is sine, we know it's going to start in the middle, then go up, then middle, then down, middle again. No matter what, there are going to be these key points that we can always have on our graphs. These 5 key points depend on what type of graph we have. So in a sine, it looks like our key points start with an x-intercept, a maximum, an x-intercept, a minimum, an x-intercept. So 3 x-intercepts, a maximum, and a minimum. For cosine, it looks like it's a maximum, of x-intercept, a minimum, an x-intercept, a maximum. It does not matter what type of key points they are, but it should be the 5 key points that are in a row that we can use to graph. So let's see if we can do this practically. Down here, we're asked to graph a sine function. The function is g of x equals 4 times the sine of x. And I want to let you know, the start of this problem involves us figuring out the amplitude and the period. Well, recall that the amplitude is just the a value, or at least the absolute value of the a value, which is 4. So this graph is going to have peaks that are 4 away from the middle. Cool. The period is equal to 2 pi divided by our b value. Well, there's no number in front of the x, so we would say our period is 2 pi over 1, which is just 2 pi. Cool, our graph is going to be exactly as wide as the parent function. It's just going to be 4 times taller because of that a value. The good news is, we do not need to plug in points anymore. Plugging in points is great, if you don't know what a graph is going to look like, but we know what this graph is going to look like because we just graphed the regular sine, and we know it's just going to be 4 times taller. So then, to graph this sine, we know that it's going to be like so. The graph of sine is always going to start off with a key point at 0, and for sine, it's 0, 0. I'm going to mark that down as, well, I'm going to keep track of them all sort of over here. An x-intercept of 0, 0 is the very start of a sine graph. Then our original sine function went up afterwards, right? It went from 0, and then at pi over 2 was at 1. So we can still use those markings because our period is the same. Our period is 2 pi. How do I know to put 2 pi all the way out here? Well, because we need 5 total points to make up a period. 1 is at 0, 2, 3, 4, 5. Our 5th point, 4 away from the start, is where the period goes, so 2 pi. From there, we can cut our period in half to get the middle. And then if this is 0, between 0 and pi is pi over 2. And between pi and 2 pi is 3 pi over 2. So that's how I got that shape. Of course, we're also going to want to graph in the negatives, but we don't need to worry about labeling that, because we know it's just going to repeat. On our sine graph, we then reached a maximum point, but remember that our amplitude now is 4. That means that instead of going up 1, we go up to 4. That way, we would have a peak 4 tall. So that is a maximum. Our maximum is at pi over 2, sorry for my hand obscuring the camera, comma 4. After that, on our parent function, we went back down to 0, so we have another x-intercept. That's another key point, pi comma 0. After that, according to the parent function, we went, let's see, middle up, middle down to the minimum. If our amplitude is 4, that means our minimum is 4 below the middle. So it should be at negative 4. So we have a min. The minimum is 3 pi over 2, comma, negative 4. And then since we go right back to 0, we have another x-intercept, 2 pi, comma, 0. With this, we can complete our curve. We have our 5 key points. This one's going to go up, and then back down, and then all the way down, and then back up again, and it's going to continue in that direction. And we know that it's going to be sort of the opposite in the negative direction. It's going to go down to the minimum, up to 0, up to the maximum, down to 0, and it's going to repeat as well. Cool! That's our sine graph. Done! Dusted. Let's take a look at example 2. I'd like you to try out example 2 on your own because it's tricky. I will give you a little bit of a hint. This one is tricky because it has an amplitude change and a period change. Just remember, your period should be the 5th point. So we start at 0, it should go boom, 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 then the period. Try this one on your own by pausing the video and come back in a minute and see what you did. So here, we get g of x equals 1/2 cosine of 2 pi x. What's our a value? Well, here the a value would be 1/2. So we know what our amplitude is going to be. The amplitude is just the absolute value of our a value, which equals 1/2. Guess what? We know how high it's going to go above the middle. If the middle is at 0, and the amplitude is 1/2, it reaches a maximum of 1/2 and a minimum of 1/2. What about the period? This is where things get really funky. The period is equal to 2 pi over b. What's our b value here? What's multiplying our x? 2 pi. Hang on a second. What's 2 pi over 2 pi? That's just 1. So our period is 1. Not 1 pi, not 1/2 pi, it's just 1. So we can make our other tick marks based on that. Halfway between 0 and 1 is 1/2. Halfway between 0 and 1/2 is 1/4. And halfway between 1/2 and 1 is 3/4. So this is super weird. This is why we can't rely on our unit circle anymore, because we don't have these radian lengths of 1, 2, 3, 4. We have radian lengths as fractions of pi. This is why it's so important to remember the parent function for cosine, and we can base our graph on that. So let's look at the parent function for cosine. The parent function for cosine starts up at the maximum. Our maximum is 1/2, so in this case, we are going to have a point up here at 0, 1/2. That is our first maximum, 0, 1/2. From there, we then go down to our middle, which in this case is our x-axis. That's an x-intercept of 1/4, 0. From there, we go down even further, down to negative 1/2, our negative amplitude, because that's our minimum. So our minimum is 1/2, negative 1/2. We go back up to 3/4, 0. That's our second x-intercept. And then at the very end of the period, where we get to 1, that's going to be another maximum. So we reach another maximum of 1, 1/2. All we need to do now is graph it and repeat it on the other side for all of our negative values. So it goes down, then way down, then back to the middle, then back to the top. On the other side, it'll go down, then way down, then back to the middle, and then up. And of course, it's going to continue forever in both directions. That's our cosine. Done. So when we're graphing these, as long as you don't have a shift to the left or to the right or up or down, just graph the parent function either taller or wider or both. Wouldn't it be easy if we didn't have to translate it left, right, up, or down? Yes, that's right, everybody. We do have vertical and horizontal translations. So remember that a translation is like a slide. If you add something to the output of your function, meaning you add something to the very end, it goes up. And if you subtract it, it goes down. Meanwhile, if you have x minus some h value, if that number is positive, like it's x minus positive 3, that moves it to the right. If it's x plus something, that means you moved it to the left. Oops, sorry, I switched these around, misread. It should be this and this. The horizontal translation of a periodic function is called a phase shift, which is like the coolest sci-fi name for a graph I've ever heard. So we have a bit of a different way of graphing these now. Some things stay the same, but some things are very different. Step 1 is going to be mostly the same. We want to identify the amplitude, the period, but this time we also want to take note of our h and k, whether we're shifting horizontally or vertically. So let's take a look at example 3. Well, we've got the following values. Our a value is 2, our b value is 4, and is this an h value or a k value? Well, since we don't have this in parentheses, like it's not the sine of 4x plus 3, we treat it like it's the sine of 4x and then plus 3. This is a k value, or a vertical shift up 3. So we do our normal stuff. The amplitude is 2, so we know that the peaks are all going to be 2 away from the middle. To find the period, we just have to do 2 pi divided by the b value. Since our b value is 4, it's 2 pi over 4, which simplifies to pi over 2. Cool, so every 4 ticks we'll get another pi over 2 away from 0. This k of 3 means that we are shifting up 3. So we are doing a vertical shift up 3. As we draw out this graph, let's keep in mind that this graph is going to be much taller because we're going up 3. So I'm going to make a big y-axis here, like so. Step 2 is to draw something called the midline of your graph. The midline is another name for the middle of the graph. Since the middle is usually at 0, but we moved it up 3 from this vertical shift, what's our new midline? Our midline is going to be at 3. So 1, 2, 3, 4, 5, for instance. Our midline is something that we should draw right away. We know our sine wave is not going to be on the x-axis. It's going to be on the midline. Y equals 3. That is our midline. Cool. So we've got our midline, we've got our amplitude, our period, our vertical shift. Now it's the same deal. We can just make our 5 key points. Remember what the parent function of sine looks like. The parent function of sine, according to the notes we did before, should start at the middle at 0. So for this graph, we should put our middle point not at 0 anymore, because we shifted up 3. We should put it on the midline at 3. So here, let me just label out these points. Our graph starts in the middle at 3. So we don't actually start at an x-intercept, so we don't need to list them. From here, we need to figure out how to scale our graph. And remember, that's based off of the period. So we start at 0. The period is always going to be the 5th point, so 1 is right here. 2, 3, 4, 5. This 5th point is going to be at pi over 2 radians. Halfway between 0 and pi over 2 is pi over 4. If we cut that in half, we get pi over 8, so that's halfway between 0 and pi over 4. And 3 pi over 8 is in between those. 1 pi over 8, 2 pi over 8 is pi over 4. 3 pi over 8, 4 pi over 8 is pi over 2. From here, we just graph the same dang parabola. Or not parabola, sine wave. I'm used to doing parabolas with my Algebra 1 students. But keep in mind that our amplitude is 2. So we don't just go 1 up when we try to reach our new maximum. We go 2 up. If our starting point's at 3 and we go 2 up, that means our maximum is at 5. So let's write down our maximum at pi over 8, comma 5. Then the sine wave follows the same pattern it always has. Goes up, then back to the middle. So we got another point on our midline. Then it goes all the way down. Since our amplitude is 2, what's 2 less than 3? Well, it'll go all the way down to 1. That's a minimum. We have a minimum at 3 pi over 8, comma, 1. And then it returns to the middle. So our new sine wave is going to look like this. It's going to look like pretty much the exact same thing, just a little bit taller, and we've moved it up. And technically, it's a lot more narrow because we vertically shrunk it. And of course, we can continue in the other direction too, going down to 1, going back up to 0. You get the picture. It's going to continue with the sine wave. For the cosine wave as well, in the next problem, it's going to follow a similar trend. We just have to find all those features we found last time. I'd like you to actually pause the video here and try to see if you can figure out how to graph this horizontal translation. I'm going to give you a hint. Our starting point is what's going to change. Pause the video, try it out. Let's take a look together. So, as always, we should find our A, B, H, and K. Our A here is 5. Our B here is 1/2. This time we don't have a K at the end. What we do have is an H value. Since it's x minus h, our h is 3 pi. Interesting. Well, our amplitude is the easy part. Since our A value is 5, our amplitude is 5. The period is a bit tougher to do here, right? So the period is 1/2 of this. As we take a look here, that means that the period is 2 pi over 1/2. I don't want to do 2 pi over 1/2. Keep in mind that when you divide by 1/2, that's the same as multiplying by 2. 4 pi is our new period. So it's going to be a longer cosine graph. We don't have a vertical shift. Our k value is 0, but we do have a horizontal shift. We have a horizontal shift, and since our h value is positive, since it's x minus a positive h value, we know it's going to be a horizontal shift to the right pi over 3 units. Okay, now this is going to be interesting. Before we set up our graph, because we didn't have a vertical translation, we know that our graph is going to have a midline of 0. So here's step 2. The midline is going to be y equals 0, since we never really went up or down. And here was our first point. Now we just have to find our key points. Well, since we know we're not going up or down for our midline, I know that my graph can be pretty standard here. I can have my 0 here. I'll go up and down to my maximums and minimums. Since our amplitude is 5, we know our maximum is going to be 5, and our minimum is going to be negative 5. But here's the deal. We have this horizontal shift to the right pi over 3 pi units. And the period is going to be 4 pi. Uh-oh. So actually, this graph here is not going to be totally sufficient for us to write on. The problem is, we won't be able to get very far to the right, and we're supposed to go very far to the right. I'm going to do this on a separate sheet of paper then. This one here should be a little bit more suitable for our purposes. So here we go. We're not starting at 0 anymore, because we shifted right 3 pi units. So, let's start counting out our period. Our period this time is going to be 4 pi units. So, couldn't we scale it by saying this is pi, this is 2 pi, this is 3 pi, and this is 4 pi? And of course, we can keep on going if we want to as well, in both directions. I'm not going to go too far, but since our period is 4 pi, we know our 5 key points are going to be here. Or at least they would be if we didn't shift over. You see, the problem is that we are actually starting at 3 pi this time. So let's think about our cosine graph. Our cosine graph usually has its start at the maximum value. Since we're starting at 3 pi, though, it means that at 3 pi, we're at our maximum value. Okay, then what? Well, we should actually start making our key points from here. 1 point, 2 points. Our third key point will be right here. Our fourth will be here. And our fifth will be right here at 7 pi. The good news is, we know how to graph this since we've done it before. It goes from up, to the middle, to down, to the middle, to up again. In other words, we have maxima at 3 pi comma 5, as well as 7 pi over 5. Notice once again that this is 1 period away. We have two x-intercepts at 4 pi comma 0 and at 6 pi comma 0. Recall that these are going to be half a period away. 1/2 period. So our period is 4. These are 2 pi away. And last but not least, we have a minimum. It seems at 5 pi comma negative 5. So here's what our graph will look like. It's going to go down. It's going to swoop back up to the maximum. And if we wanted to continue this graph, we could repeat the pattern going the other direction. Middle, down, middle, up. Now I'll put another middle on this side just because it'll continue in that way as well. I can put another middle here. So our graph is going to look something like this. It's going to go down, back up. There's our original. It's going to go down, and we know it's going to continue in these directions. That is our new graph. That is the graph of 5 times the cosine of 1/2 x minus 3 pi. Done. Whew boy, that was a bit of a tougher one. So let's actually go to the last page here of our notes. The last page of our 9.4 notes talks about reflections, and I've got some good news for you. Reflections work the exact same way they always have, with no differences. So if we wanted to reflect over, for instance, the y-axis, the x-axis, we would just flip it upside down. So if we wanted to reflect this, it would go from going up, then back to middle, it'd go down, then back to middle. So it's the same thing, just reflected upside down. Of course, keep in mind that you can also have horizontal reflection as well. A horizontal reflection would mean that we are flipping, instead of going forward to go up, we would go backward to go up. So let's see what we can do with example 5. Again, this one is one that I want you to see if you can do on your own. Pause the video here. See if you can find the amplitude, the period, the horizontal shift, the vertical shift, the midline, our 5 key points, and to see if there's a reflection. Pause the video and see what we can do. So, let's take a look. Our A value is negative 2. Our B value is 2/3. Our H value is pi over 2. And our K value is 0. So that means we have an amplitude of 2. Remember, it's the absolute value of your A value. The period is going to equal 2 pi over 2/3. That's a little rough, but remember, dividing by a fraction is the same as multiplying by its reciprocal. So this is actually just 6 pi over 2, which is going to equal 3 pi. Our horizontal shift, we have a horizontal phase shift, or a translation, pi over 2 to the right, and we don't have a vertical translation at all. So that gives us that our midline, luckily for us, is just going to be y equals 0, just the default. Okay, we're starting to build a picture of what our graph is going to look like. Since we moved to the right, I'm going to leave some space on the right for our graph, but we know we're starting at 0, the amplitude is 2, so our maximums and minimums are going to hit 2 and negative 2 respectively. Again, we're starting at 0 until we do our horizontal shift, and our period is 3 pi, so every 4 units we go, is going to be another 3 pi, or another full period. So 1, 2, 3, 4 would be 6 pi. This one's a bit tougher to label, but remember that halfway between 0 and 3 pi is 3 pi over 2. Half of that is 3 pi over 4. And over here, if we wanted to get some pi over 4 measurement, well, 3 pi over 4, 6 pi over 4, this would be 9 pi over 4, and then 3 pi. And then we can keep counting by pi over 4s. This one here would be 15 pi over 4. If you're curious about where I'm getting this pattern, 3 pi over 4, 6 pi over 4, 9 pi over 4, 12 pi over 4, 15 pi over 4. We're counting up by 3 pi over 4s. So this would be 18 pi over 4. But that can be reduced to 9 pi over 2. This would be 21 pi over 4. And then 6 pi. Cool! I'll even put a point over here just for good luck. This is a sine graph. So we know, no matter what, that we are going to be starting at the midline. So our midline is y equals 0. We know it's going to be at a height of 0. But we've got this horizontal translation to the right. Uh-oh. We have a big, big problem. I don't see pi over 2 on my graph. Well, I do see 3 pi over 2, but how could that help us? Well, it means that every 3 mini tick marks will get to a 3 pi over 2, right? So we can actually subdivide our period even further. If we subdivided it, this would be 1 pi over 2. This would be this would be 3 pi over 4. This would be 3 pi over 2. This would be 3 pi over 2 here. I apologize. I completely messed up the scaling on this one. But the idea is that a pi over 2 is a third of the way to 3 pi over 2. So this would be pi over 2. This would be 2 pi over 2, which is pi. 3 pi over 2 would be right here. Again, we can cut up into thirds for this next portion. 3 pi over 2. We can go to 4 pi over 2. That's just 2 pi. 5 pi over 2 would be this denomination. And then 3 pi. So we can basically cut these up even further into thirds to find some more exact values. I'm going to do so by showing these lines here as our 3 pi over pi over 2 starting places. So we have a horizontal translation pi over 2 to the right. And because it's sine, we're starting at 0. So finally, we have our first point. Now remember, originally we want 5 points to get to our period of 3 pi. Since we shifted over pi over 2, we actually want to get all the way to this tick mark right here. So what measurements are we going to use to go with 4 more key points? Well, we're going to use pi, we're going to use 2 pi, we're going to use 5 pi over 2, and then we're going to use this one over here, which should be 6 pi over 2. Or sorry, this one here is 6 pi over 2. This should be 7 pi over 2. This would be 4 more tick marks, so we'd have 5 key points. Our key points are at pi over 2, pi, 2 pi, 5 pi over 2, 7 pi over 2. Cool beans. Let's make it happen. So, as we go through with this, we see that we have the following. A sine wave would normally go up, but it's a reflection, so it's going to go down instead. We go down to our minimum. Right? From here, we decide to go up again. So we go up again to our x-intercept. From here, we go up again to a maximum, then back to middle. This time our sine wave is going to look like this. Done. And of course it'll repeat. That one was a bit of a doozy, but that concludes our notes for today. So thank you so much, everybody. Have a fantastic rest of your day.